Okay, let's get started. So today we're going to introduce different types of usage of deep learning, that is detection segmentation. And here's the outline. So we'll introduce the concepts, and there are several examples of networks for detection and segmentation will be introduced, like UNO, Carson into last person, and it's a series. So far, let's review a little bit what we have previously. We know that deep learning actually started from the classification problem. But by training the neural network for classification, we can actually learn a good something we call feature maps, or in some weird they call representations for images here. And so in that case, we can use it for retrieval because it gives us different type of features. It's one we have learned so far. However, there are actually a wide range of tasks we can use deep learning. And so that's the reason today we're introducing another set of commonly adopted networks for detection and segmentation. So let's recall the facial recognition. I guess this is most people are familiar with facial recognition. And when a user presents in front of a camera takes a picture of that person, and the face will be located, and the identity will be recognized. However, during that process, facial recognition is not the first step. So you got to conduct the face detection first to find where the face is. So that's the face detection part. Facial recognition is something, yes, the technique is a classification problem for sure. But for face detection, we haven't talked about it so far. So how to locate object you're interested in the image. So we haven't mentioned that part. So today we're going to move forward for that part. And the face detection is something you're really familiar with. If you're using some of your cell phone taking pictures, and you will see that there is a usually green box and tell you where are the faces. So this is actually face detection technique. Sometimes we call it detectors. So and that's what it is. Because it's assumption like face need to be detected first before you can actually conduct facial recognition. So starting from very early age, the researchers have put a great efforts on the face detection. So this is one of the early methods. The early method, this is actually before deep learning. This is actually quite popular and quite successful method. You can consider they are doing some they stack a set of filters, like the filters we have so far, like edge detectors. But those detectors are, you can look at it, it's specifically designed for, you could consider their line detectors, to find the difference of left and right, up and down, and in the diagonal orientations as well, and there are some vertical line detector and horizontal line detector, diagonal line detector, or something like that. Anyway, there are different types of detectors, and there's assumption like the face is just such kind of combination of those lines there. So by stacking those different detectors, you can actually detect the face very well. That's a very early method. But compared back to the deep learning, I guess the ideas quite alike to each other, right? Right now, we're stacking convolutional layers, and in terms of convolutional layers, it's also stacking layers, and in each layer, the kernel is used as filters. So we're stacking the filters as well. But the difference here is in previous method, you have to design specifically how to stack such kind of filters. You have to come out a set of sectors, orders or something for stacking that filters, and for each of the filters you design in advance. They are with a certain kind of function, like what I have mentioned. But in deep learning, when we're stacking the kernels of filters, and network will figure it out what filters to use, what kind of kernel is the best, what is the best way for stacking them together. So this is a difference. The idea is quite similar. Also, this anyway worked very well previously, but because it's relying on the human knowledge for stacking layers and for design those filters, it cannot be generalized well because it's so complicated. Anyway, there are many combination of lines there, and in different conditions there, you have to change it and it takes a lot of effort. So, but deep learning makes it very easy. So, but how we can use the idea, use the deep learning for face detection, So, like in a very general sense, deep learning is like you feed some data into the network, and the network will give you some kind of outputs there, and you evaluate that output. So, from very general sense, let's see, here's already some kind of layers of neural network there already. So what we have to do at the very beginning is just feed that image into the network. This is the same as your doing for classification, right? However, detection is not something like there is a label, like here's a cat, here's a dog, and here's a face. Even you can get a label, like there is a face there. But but the problem is you need to know exactly where the location of that face is. Maybe you're able to do the classification for the semantics or conceptual faces, but you're not able to do the localization. So that's where the problem is. We can still so come to here. The problem is how we can let the network or say it in another way is how we can convert the localization problem into a classification problem. Or in a more general sense, neural network is something, some tools for us to make predictions. How we can make network predict the location of the faces, right? So here's the problem, and here I would like to introduce it today is it's quite popular object detection, and there is community working on that continuously. Right now, they have ULO 8 already. But what we're going to introduce today is the first version of ULO. It's it has been proposed something like 7 years ago, 6 years ago. So that and people keep working on that. So they improve it. Right now, the performance is much better than this original one, right? But we will take this as an example because the basic principle is the same, and this is much easier to understand. Later, they added a lot of engineering stuff to improve the performance. So let's see what ULO is. As I mentioned, network can help us to do the prediction, and we have to let the networks know what kind of prediction we're expecting. In case we can generate some kind of labels for those kind of detection, then we can construct loss function to evaluate the machine, the network's prediction with the ground truth, right? So we can calculate the loss, and we can rely on the gradient descent to figure out the best prediction and best network, updated network. So this is what ULO is doing. First of all, you can divide, you can split a slice one image into S by S grid. So there are many patches here. Right? Once you have this patch, you can first of all, you can consider, you can conduct classification on each of those patches, because we are going to, let's get back here. So the first, our goal here is trying to figure out those different objects in that image, right? So we're going to know the semantic, we're going to know the label. Let's call it class label, like the person, like the dog, like a horse, or something like that. Those are still classification, right? So we let's start with that most straightforward part. Once we have those patches for each of the patch, we can conduct a prediction for its class label. Like here at this position, it belongs to the dog, right? We needed to give us a prediction of dog here. So in an ideal case, right? That's a dog, right? And here's a bicycle. And there are other objects as well. So for each of them, we can do a prediction using exactly the same what we had introduced previously. So that part is easy. You just gave a label. The label here, class label, could be something like we call it one hot, a multi-hot vector. So let me draw it very. So for here, you can actually let's see. Here is a vector, and each of the elements corresponding to a class, like a person, first one, the second one, a dog, or something like that. And we set it to 1 here, because the second position is for dog. Then that prediction is, here is a dog thing, right? And if the corresponding position was set to 0, meaning that that concept doesn't exist in this image. So in case we just have 1 here, and we call it one hot. One hot. It's a vector. So one hot. And in the future, for each of those patches, we can consider this as a ground truth. Because we know for each of them, like here, we know it's a dot. So this class label for this patch will be something like that, right? So this is a ground truth because we know there's a dot variant in that patch. However, the prediction network made may not be exactly the same. So most likely, they are going to predict a vector, something like in the first element, it could be something like 0.1, and the second one could be 0.9. And the other might be also quite small, 0.02 or something, and so on and so forth, when the network make a good prediction, right? So here again, here is a prediction, and here is a ground truth. So prediction. But we can compare actually these two vectors to evaluate how good the prediction is, right? Is this clear? Do I need to see it again? It's okay? Okay. So you have prediction of one hot, and you have a ground truth as a one hot vector as well. So you can compare it to see how the prediction is. In case they match very well, so the prediction is good and the loss is small, right? In case they're quite different from each other, the loss is large, meaning the prediction is not so good, right? So this is for the semantics of that patch. However, this is one, and actually what the UNO is doing, because you can repeat that process for all the patches, right? So for all the patch, you have an output of a class label. However, at the same time, we can have it to output another thing, a prediction of the location of the rectangle. So it can be done like, because to output the prediction is quite easy. You can, let me explain how we can do it. So for making this prediction, how we can do it. So basically what we're doing is we have a set of neural net convolutional networks. We probably have some FC there after. And for the last layer of the FC, we can put exactly the same number of neurons as the number of elements of the one hot vector, right? So this is, so meaning that like at the end, this will be your prediction and they're fully connected. So, okay. For each of neuron, you have a number there. So this, the last layer can be used as a prediction, the output prediction, right? However, this is easy. This is what we have for classification. But how we can make it to predict the locations? Any idea?
and we add the location and the feature of the outcome to the data.
Right. Yes.
Like the,
Then how we can do it here?
like we add the coordinates x and y and
Yeah.
the gradient behind all the bounding box.
Okay, that's great. So the solution is quite simple as you mentioned. So what we have to do is just add some additional neurons in the last layer, right? So in case how we can describe those bounding box or rectangle, probably we just need this center coordinates, and at the same time we need the width and the height of it, right? So we can use that. Let's see, this one way we can. The center is a number, and the y is another number, right? And the height is also another number, right? So what we'll have for this one is x, y at the center, and a y and a height. So this basically describes a rectangle in that image, right? Those are just numbers. They actually, from the network perspective, they don't have too much difference from the other predictions. So what we can do is just add. Let's just add something. So in case we need 4 numbers, then we add 4 neurons. And we know that we will we'll use the neurons before that as a prediction for the class label, and we will use the other 4 as a prediction for neural network, for bounding box, sorry, right? So those are going to give you numbers. At this moment, you can totally ignore how good it is. Maybe at very initial stage, it's just random, right? It gives you some random number, which may not make sense. However, we can do the same by adding what we have, the exact location as a ground truth. Because we know what exactly, usually we labeled it, we know what exactly the dog is, what exactly bicycle is, right? So we can, let's say we have ground truth for this. We can use this parameter to here as a ground truth. Then we can compare those ground truth values to the prediction as well, right? So we know how good it is, right? So then in that case, we can, in case we know how good it is, so we can construct the loss function, and we can send it back for back propagation using the gradient descent. And the network will update, they will do better here for predicting the bounding box, right? So this is what exactly happened. You can see it's just that easy. We just add more neurons and we extend the ground truth with the numbers for the bounding boxes, and the rest just for the same. You don't have to worry about it because the back propagation is going to figure that out. This is what exactly happened. So you will see here, there are actually a lot of bounding boxes there. And also at the same time, you will actually add a confidence score for each of those boxes, meaning that like the network will predict the location of the bounding box, and at the same time will tell you how confident it is about the bounding box, right? Like in the previous slides you see here, we have a prediction of bounding box. At the same time, it's 0.64 that's the confidence score for that bounding box. Okay, this basically, you can repeat that process, meaning that for each of those patches, you have the prediction for class labels, at the same time, a bounding box, and at the same time, you have the confidence score. Okay. So that's what UNO is doing, but it's not all. It's just for making initial prediction. And here's another example which explains in more detail about what UNO has done by giving the exact number. You could see here, this A is equal to 7, meaning that when they're dividing them into patches, it's 7 by 7. And the B equals 2, meaning like actually for each of the patches, they make 2 prediction, meaning like 2 bounding boxes actually. So, and you know, for each of those bounding boxes, need five parameter to describe it. Like I mentioned, you could use the coordinates of the center and the width of the height. There are 4 numbers, and plus the confidence score, there are 5 of them, right? Then so on and so forth. And and C equal to 20, meaning there are actually 20 class labels there. Okay. So up to here, is it clear enough? Because it's kind of different from what we had. So I'm taking more time to introduce. Anyway, you can see, UNO can give us an initial prediction about the bounding boxes and class labels, competences score as well. However, this is what you are going to have after UNO, because for each of the patches, they have their own prediction. Those predictions sometimes overlap each other. So we have to sort those predictions to merge them into what we want. So here's a very simple algorithm called non-max. So it's started quite simple. Like at the very beginning, you started from any of the bounding boxes. And from that bounding boxes, you check those are highly overlapped with it. So it would be something here, something here. These bounding boxes are obviously for the dog, right? So you check for the exactly class label and those highly overlapped one, and you figure out this group of bounding boxes, then you will move to the most confidence one there. Then you discard the rest of the bounding boxes. Then it will give you something like here, because that's the most confident one for dog, right? So you're going to have this. Then you can repeat that process. Then after that, you basically have already discard this bounding box, and those are another related to dog, this yellow box as well. So only this green one left. Then after that, there's no overlapped bounding boxes for this final one. Then you started from another bounding box, repeat that process. Then here you could see this property, you move to this bounding box and you repeat that process, find the most confident one and remove those with a large overlap with that bounding box. You discard them, then you're going to have this one. It's basically the same procedure. It's quite straightforward one, right? Then in that case, you will have something like that for different class label. Okay, this is because it's kind of different from what we have previously, so I've taken more time on it. Let me say it again. So you have divided the image into different patches, and for each of the patches, it made the prediction for class label as one path vector, and at the same time, it's extend that prediction with additional neurons for making prediction for bounding boxes as well. So putting them together, you can compare between the prediction and the ground truth figure out a sort of initial prediction, a lot of bounding boxes here, and the class label as well. So another thing I forgot to mention is when you're this prediction of that, sometimes a student ask that question. We just have this very small patch, but how can we make the prediction of the bounding box is larger than it, and also some kind, maybe it's at other location here, right? So it doesn't matter because the neural network don't know what they are not prediction based on its own location. For them, it's just a sort of numbers. So because the gradient descent will push them finally making a better prediction. So meaning that like this box is trying to predict this one, and the other box related to the dot all trying to predict the same bounding box. It doesn't matter. Okay, then you have initial one. Then you run a non-max algorithm to remove those highly related, highly overlap that one. Then you have the final result. And to evaluate the overlap, there's a term called IOU, which means intersection of overlap area, something like that. You probably see it in the paper already. Okay, that's it. So that's the procedure. Here we just make the deep neural networks able to make prediction for bounding boxes. Is that clear? Okay, great. Thank you. And now, however, this is good. We can tell the bounding boxes. However, in a lot of applications, it's not enough because it's just a bounding box. And sometimes we need to know the exact pixels related to some objects. And in that case, we may need something we call a mask. Like for this long area, we need to know the pixels related to it, right? So we need a mask for a brain. We need to know different sections related to something, right? So meaning like that a bounding box is not enough to describe the information we want. So we call this segmentation, semantic segmentation, meaning we're not only looking for bounding boxes, we're looking for some of the regions in that image. So we're going to use the very similar structure of convolutional neural networks for that. How can we do that? So for bounding boxes, it's easy. We just need a set of numbers to describe it. And as we have mentioned, 5 numbers can describe it. And so we add 5 neurons there, right? This is quite easy. However, right now we need the exact pixels for them. are we going to add more neurons here? Because sometimes the region just consists of different number of pixels there. Meaning that like it's not easy to know how many pixels are there in a device. So how can we do that?
Can we add one label?
One label?
Yeah, so for example, if this object is inside the segmentation, label it as 1, and otherwise it's 0. So,
You mean for each pixel,
yeah.
you have a label, right? Okay, that's a good idea. That's a good idea. Yeah. It's pretty much like that. As she said, we got something like a label. That's a good idea. In case it's a label, we're going to have some kind of label image. We could call it label image. It's actually a mask, right? The mask can be considered like this one. This is a mask, right? This one is kind of label. There are two numbers. There are two possible values for each of the pixel of that output. It's either 1 or 0, right? In case it's 1, it's the region we're looking for. In case it's 0, and it's not, it's out of our entries, right? So these are considered some kind of output, because you know in the neural network, especially for the fully connected layer, the shape doesn't matter that much, because you know we have those one hot previously one hot vector out and outputs. We can put the last layer as neurons as a line corresponding to this output. This is quite straightforward. However, we can to implement this way, we can do it in different way. Like we can put the exactly same number of neurons corresponding to different pixels of that image. Meaning like those are probably for the first column of this image. And we have another set of neurons, okay, which might corresponding to either those pixels. Anyway, to make it easier, it's okay. Just flatten them as a line. So this is one. And at the same time, probably we can do it as a 2D image as well, because in different layers, they are just, you can consider it as a one channel feature map. That feature map has exactly the same size as an input image. This is one possible way. So this here for each of them, it's just a result feature map. And each of them has a number associated, like 0.1, 0.2, 0.9, or something. Okay? So in the last layer, we can do something like that. So, and after that, then we can use this. This is actually the output we are looking for. We can use a mask as a ground truth. Sorry, it's not easy to resolve with the mouse. So it's awfully scares me. Oh. Okay, so in that case, the ground truth will be something like If they are out of interest, they are just 0. If they are what we're interested, we will put 1 here. Right? So right now you see we are able to compare between the prediction and the ground truth, and we can even evaluate how good the prediction is. Right? So these are converting back into the framework we have for classification, right? So, I'm just trying, not only telling the solution, I'm trying to tell you a way for building solutions, like, because what's most important is the deep networks are able to help us to find the best parameter as long as you can construct the prediction and the shape it can take, and also you can evaluate that prediction with some sort of loss function. Right? That's as long as you can do that, you can use the neural networks. So that's the reason people figure out different ways to solve it in different scenarios. So even right now we're talking about segmentation, semantic segmentation. So that's let me say it again. So right now we have the object detection for predicting bounding boxes there. There are semantic segmentation there as well, and which tell you most of the time tell you the foreground and the background stuff, meaning there are just something you're interested in, something you're not interested in. It's like a binary classification. However, there are certain another set of things called instance segmentation, meaning you have to find the pixels related to different objects. Even here you see they're all people, but there are person 1, person 2, person 3 there. You have to distinguish from different person. So that's called instance segmentation. So, and okay, let me just introduce a very popular neural network called UNet. UNet is a network. You say the shape is a U. Oh, it's called UNet. And so UNite, let's to understand how it works for segmentation, and you can simply ignore the structure first. I will introduce the structure later. So let me throw something for you. Okay, there it is. So you can consider here's a convolutional network. It's very similar to what you have. The UNet work like you have the input image. Maybe there is some kind of animal, and you want to look for the region corresponding to that animal. And so in that case, in the last layer, it outputs something as a feature map, and it will give you something like those are all probably all 0, and the central part are 1, and probably the central part would be something like this, like I have mentioned. Probably gave you something like that. Those are 1, the other are 0. So, and at the same time, you have a ground truth because during labeling, you know where the animal is located. So, and then you have predictions. You have ground truth. You can compare them pixel-wise to see how good it is. Right? Ignore the structure right now. It will be something like that. you have a sort of network after you to do the convolution, and output another feature map to compare the feature map. Use that feature map as a prediction and compare back from truth, right? So this is exactly the same, something we're familiar with, right? So let's move on with that. Let's take room in to see the structure. What UNet is doing is for this half of the network is doing downsampling, meaning that like after convolution, because convolution usually will shrink that image, right? They shrink that image step by step. So they shrink that image to smaller size. And then they can use convolution to expand that as well. So they do that upsampling to enlarge that image. So those are trying to shrink it. These are trying to, you can consider we're reconstructing it. So there are two parts, shrinking and upsampling. Then you will have a prediction, something like that. So what's the rationale behind? What's the rationale behind? Any idea? Why it works? It's quite successful, actually. It has been proposed something like 80 years, but nowadays people are still using it for segmentation purpose. Why we have to do a downsampling then after upsampling? Then it just succeeds.
It sounds like the shift detector use. We try different scale, different.
Okay.
Yeah.
Yeah. So he's relating to the shift. That's quite good. In a shift, we try we investigate the feature at different scale. As we mentioned, at different scale, it's actually imitating you're observing an object at different distance, right? So this, from this perspective, the UNIT are able to do something similar. When you shrink it, it's something like you make the figure, the image vacuum, right? But once it becomes vacuum, meaning there's no details. But at the same time, you get the overall shape of that object, right? So it's like we're standing far away looking at some of the building. We just roughly know, oh, there is a building. The other are just background. We know something like that. But this is some kind of information we want, right? To do the segmentation, we need exactly something like that. Maybe for a certain image, it's the best for you to look at a certain distance, right? So those downsampling will help us to do that, right? So in the upsampling part, it will reconstruct its original resolution, so it can be compared back to the original image. And at the same time, when you downsample it, you got some rough idea about the shape, right? By reconstructing it, you add some details as necessary. Those as necessary means like you're going to make the prediction more like the ground truth, right? The back propagation of gradient descent will tell you how much detail is the best or enough. So this is very good. This is one perspective of that. So a very similar way to looking at it, when you're shrink something, you're getting something like a general information of that image. And then by upsampling it, you are adding some kind of details. So this is the rationale of the unit. And at the same time, you could see there's something called shortcuts. Does that remind you something? Why we have to add some shortcut here?
It's something similar as ResNet.
Yeah, that's right. So yeah, that's very similar to ResNet. And at the same time, you could consider like this is a kind of condition for that risk construction in a way like in the future, the construction they're not only rely on those results because it may lose some of the details by purely going along this path. But this one, because it's that's resolution, the details are reserved better than the one reconstructed from here. So this will help to give you more details. This is another way of looking at network. Okay. Okay. Thank you very much. Those of you are actually thinking about it. And so this is a unit. Maybe we can take a break. It's already 4:26 and come back like 4:35. We will continue. Okay. Oh, there's another thing. Actually, we already have the assignment 1 mark. So we will release that result tonight, and you will know it very soon. However, you might will have some question about the marking. Let's do it something like this. We're planning to have a make-up class because we actually have one holiday. We skip one lecture. We're going to arrange one make-up lecture for that. Another situation is in the April 5 or 6. It's a holiday, right? It's Wednesday as well. So meaning like we're going to have another schedule of the class. We're going to arrange another makeup for that lecture as well. So but I don't want to put these lectures too close to each other because you need some time to digest the content of every lecture. So I'm going to arrange the first makeup class tomorrow night, Thursday night, or something around 8. I guess is that okay for you? Something around 8 during night for making up the class. However, I'm not going to put. I'm not going to give the content of some of the content. I don't want you'll be overwhelmed with content. So I'm going to take that class to explain some of the idea of the assignment 1, the common arrows and something like that. And at the same time, we will release the assignment 2 tonight as well. So it's also 1 week, you can do that. And I will introduce a little bit of the assignment 2 later there. So during that makeup class tomorrow, we can discuss the solutions of the assignment 2 as well. So in case you have any questions there, you can ask during that makeup class. And to get you better prepared for assignment 1. Actually, I see a lot of students are doing very good in assignment 1. You need to keep doing that. And then assignment 2 is very, I guess, will be easier because they really have assignment 1. So what you need is very similar to assignment 1. But in case you're really familiar with, it might be easier. So, okay, let's take a break.
体位上，就他们的那个图报，然后我们那以后对，然后我们看，你忘了不会那些。就是一开始我对。讲了。
所以它是一个
一个人的衣服。你这个要问张子吗？你问我不用啊，张子才是学霸呀。你问我等于这个问错人了，学霸在你旁边，他才知道自己的学霸。就是垃圾，啊，第一个是第一个啊，对啊。那就是一个3个尊重的，真正看考试。看见那个资料，我说有个都没给你送过去，你也没让我也没上。还有我也超评是，我下面有个其实我觉得这个拿新经理还挺有意思，设计你上一下这个。啊，这个可以上一下。
Let's just continue. But during break, I got very good questions from students. So I want to share here. So one thing, one student recognized the connection of the segmentation with what we have for morphologic operations, right? So when we're doing the coronavirus detection, it's kind of detection, but at that time we're designing the structural elements by ourselves, right? And we apply that structural elements on that image to figure out what's the best object locations. So this is pretty much like that, but the network has helped you to do that. You can think that in that perspective, and those two things have been connected. That's also the reason when I'm introducing the morphological operations, and I said several times asking you to connect back to the filters, right? There are just filters as well, but with different operations. This is one good aspect, and I appreciate it. And you realize that. And another thing, maybe a little bit confusing here, maybe say it again. So this network will, how it works is it's actually how it's related to the deep neural network learning. So this is input. This input will go through a set of convolution here, 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 and so upsampling here, here, here. At the same time, we have some shortcuts there, you know. So these are feed-forward process, and finally you have the prediction. So this is feed-forward. However, what is not that intuitive here is the back propagation. So the back propagation will be something like when after you compare these two, you have a loss evaluated, and based on that loss, you can calculate the gradients to different parameters. And I'm using this data representing all kinds of parameters. You know, as we introduced, as long as you know the connection and you can use the chain rule to back propagate that gradient, right? So the gradients will go something like go back following that feed forward process, update all the parameters along the way, and also it will go through the shortcut as well, all the way back for updating the parameters. And in that way, the back application still updates the parameters of this neural network. That's the way how we are doing that. Even this unit is not in the shape we're familiar with, because most of the time we're having this, they're just around the same time. But this is actually the same. Another way you can look at it is you can flatten it. After you flatten it, and you will see something very similar to what you're familiar with. So it's still aligned, but the difference is you add shortcut here, something like that. So it can be drawn in the same way we're familiar with. And when you look at this one, I guess you understand what it's for. The feed forward and back propagation, right? Okay, this is something I want to share. Okay, let's move. We still got some stuff to introduce. So here you can see in the detection by looking for the objects, we're easily looking for the bounding box or asks there as well. And how about is there something like we can some kind of network we can do both. Or so in that case, I would like to share another set of neural networks, which are also very popular for detection segmentation. So the reason I'm putting it here is you could see a development of the process from detection of bounding box to a segmentation, and how they do it. There's some quite interesting idea has been built in between. So, and the first one is RCNN. RCNN is something like the region specific CNN. CNN just convolutional neural networks, right? So the target is to detect the bounding box. Like we're looking for the bounding box for this cowboy, and how can we do it? So they propose a very straightforward way. No, that's something like 10 years ago. You see it from here. So at that time, is still people deep learning are not that popular like nowadays. And at that time, there's another very popular classifier. It's SVM we have introduced. SVM taking over the popularity something for something like 10 years here. And later it gives its place to deep learning again, to neural networks again. This is actually the third time neural networks getting popular. And there are two, it has been popular previously for 2 times. And this is actually third time. So, you know, technology developing continuously, even nowadays, neural network might be very popular, but we don't know what will be popular in the future. But you could see the basic principle wouldn't change, like I mentioned in lecture 1. Okay, let's get back to here. We need to detect a cowboy. But how can we use the neural networks to do it? And these are, it's kind of we use a very different way and quite straightforward way. And most important, and they don't actually use the CNN for classifications either, and they're using SVN. But even they actually use the CNN for getting the features there. What they are doing is, first of all, you need to extract the regions first. So this is, they're doing it in a different way. Like in the we're trying to let the network give us prediction about the bounding boxes here. But they start with some box. So meaning like you can sample some boxes from the original image. And there is something called random sampling. Random sampling is a method by randomly sample some rectangles or regions or bounding boxes from an image. Meaning as like you can extract different parts from the original image. So in that case, you have multiple regions, right? So they're going to figure out the regions they want from those sub-regions. So this is the idea. The rationale here is something because in random sampling is a process. Well, it's actually not purely random. Even the name is random sampling. Every time when there are sample subregions, they will evaluate the objectness. Objectness means how possible it's an object. Like when you're having a picture, like those areas, because the change of the values are smooth, right? It's with no confidence, this contains an independent object, right? But when you're looking at something like here, probably it's an object, right? So you can use very traditional statistic way to evaluate how possible is an object. So anyway, the random sampling consider the objectiveness, meaning the regions sampled are more or less contains one object there, even not exactly. So they will solve that problem. You will not sample this perfect bounding box there. You are subsample some of the bounding box which cover some part of this target you want, but later we will combine them. So, the first step, use the random sampling to find the subregions, and for each of the subregion, it's an image, right? So to feed this image into a neural network, and neural network are pre-trained for a classification problem, but they are not using it for classification. They can take the feature map, like what we have done in retrieval problem, as a feature vector for this region. So in that case, for region 1, you've got one feature vector. For region 2, you've got the other feature vector. So they get a sort of feature vector there. Then they will use that feature vector to make prediction. So if you're looking for a person and it's just became a classification problem, right? As mentioned, they're actually using SVM because you have the feature. You can rely on a feature for classification to see how possible it's a person, right? So it's a classification rather than the localization problem. They actually has converted the localization problem into a classification problem for subregions, right? Because they've really has done something like split objects by using the random sampling. In case the person is detected, meaning like they have a very high confidence score at the end, and this subregion might contain a person there because they already have a subregion. Then, but as mentioned, may not be perfect. So they figured out a way to merge different regions. And this is process. The sample, the X, and this is for send feature to SVM to classification. And last step, you have, let's see, you probably sample something from this person, like, let me draw some rectangles. And you sample a net, a bounding box from this cowboy. And those bounding boxes all gave you a prediction of a person, right? So meaning like those are all possible bounding boxes. Then it turns out you have to merge these bounding boxes as a whole to get the right prediction, right detection of the location, right? So how we can merge them into the one we are looking for. So how we can do it? Any idea? Better to think about it because, as I mentioned, not painting the solution. I'm trying to help you figure out a way to build solutions in the future. That's more valuable. How you can do it? In case already know certain bounding boxes there, then how we can merge it and into one, and given, and also given the condition like we may have a ground truth bounding boxes there, we can compare that. How we can do it? And
You could just take the maximum value of every coordinate and make a big bounding box surrounding all the other.
okay, that's one. Meaning like you're actually find the maximum possible region to cover your findings, right? That's one possible way. That's good. You can cover that object, but it's not that accurate. The disadvantage of that. You know. Okay. Okay. Good. Okay. Yeah. Okay. So he's saying like we can find an overlap, meaning the intersections, the common intersections of those bounding boxes there. I appreciate these two answers. One exactly find a very aggressive, find the maximum possible region to cover the object, and he's kind of conservative to find you're actually looking for something like minimum region, right? To more accurately locate that object. That's also both a very good idea. Um, oh, that's very good. But one is very, as mentioned, one is a very aggressive, another is kind of conservative. So what exactly they're doing here is we can use the regression, as mentioned here, boxes regression. So so we actually have this term a lot of times. I'm not actually sure your understanding about regression. You supposed to already have it in the statistics course, right? So maybe in the statistics, you are probably having it this way. Okay, so most of the time, it has been taught this way. So you got several points here about the x and y. This is kind of relation between x, y. You have some samples, then you're trying to find a line which can represent those points by using the MSE, by measuring the distance of this point to this line. And finally, you're looking for a line which can have the maximum sum distance of that to that line, right? Of this point. Is this what you? I guess this is what you learn from the statistics, right? So, what we're going to do here, actually, it's the same. It's the same. We can use the regression to do that. Regression is like you're giving some data points. You're trying to use a model to fit it. So you're looking for the best fit line there. If we're taking that from different perspective, if it's multi-dimensional, we're actually looking for something which have the maximum distances to all other points. So it's something like the mean there. If it's just one value, it's just one point, it will be a mean, right? If it's a line, then it will be something like that. And also at the same time, you can actually extend the idea. You can use a ball in 3D to summarize a set of points in the 3D space, right? So it's just how your model fits the data. This is regression in a more general sense. You can build a model, you can evaluate how well that model fits your data. So what we're going to do here is we're looking for a rectangle which will fit those predictions the best. So we're looking for something which fits them the best. right? So in that case, we can do it in different way. Like we can regrade the top left color. We can regrade the bottom left color, and we can regrade the centers as well, right? So in this case, it will gives you a best fit in terms of regression, and it's probably complement solution like they have proposed. It's not that aggressive, and at the same time, it's not that conservative. Right? Probably because it's kind of find a balance in between those two, and also it's statistics based. So this is what exactly they're doing. After you have those proposals, they're going to summarize that proposal into one prediction. Then they can compare this prediction with the ground truth. And the simplest way for doing that is just measure the overlap between those two, as I mentioned. In some paper called IOU. Yeah. So you can conduct the learning to find the best fit, the best way to fit that breakdown. So anyway, this is what they're doing. Let me say it again because take a lot of steps. First of all, you have an input image. You do the subsampling, find the sub-regions, and for each of that region, you use the CNN to find the feature. Then you run SVM to do the classification. Then you could know all the regions related the objects you're looking for, like the person, right? And you're taking out all the sub-regions related to person, and then you do the regression to get a final prediction of that location. So this is what they're doing. Quite straightforward, and even it's multiple states. It's not that decent compared back to a deep neural network. The deep neural network sometimes they would like it to be end-to-end. This is another term used. End-to-end network, meaning like you have input there, and after you feed it into neural networks, you have your output at another end. You don't have to do something extra to make it happen. But here, definitely you see there are many efforts. You need to run this random sampling. You need to extract feature by yourself and feed into the SVM. Even you can program to stick them together, but it's considered multi-stages rather than end-to-end. Okay. This is a feature, end-to-end is a feature appreciated in deep learning a lot. Okay. The RCNN is straightforward and good. However, there are disadvantages there because it's too time consuming and also consume a lot of spaces. The reason is, what's the reason? What is the reason?
Too many bounding boxes and the feature structures will be
Okay, that's very good. That's exactly the reason. You got too many regions because random sampling usually gives you a lot of boxes there. If you have ever tried bounding boxes, it's not like what's on there. Usually they will propose 1,000, 2,000 bounding boxes for you. Meaning like for one image, you actually have to feed them into neural networks for 1,000 times. It takes a lot of time. So to address that problem, and they further developed this RCNN, the same author has made the fast RCNN, meaning it's faster, a fast RCNN I wouldn't use the faster RSN because later they developed a faster RSN there. You will see soon. Let me introduce the faster RSN. The idea is you just have to feed this image into that network once. Because as we mentioned previously, the feature map, the spatial dimensions of the feature map were more or less preserved with the correspondence to original image. Meaning like for certain position in the feature map, you can find the correspondence in the original image, right? Because after the random sampling, they're still using the random sampling. After random sampling, you got different regions there, right? You got the coordinates of the bounding boxes there. And based on the spatial correlation between spatial dimension, you can actually exactly find what specific region, for each of bounding box, you can get a certain part, sub-regions from that feature map directly. You can use that part as a feature rather than to run it again into a neural network. So that saves a lot of time because you feed it once, you got one feature map, and you got some sub-regions from that feature map and corresponding to the original bounding boxes there. You can use that directly. And at the same time, they discard the SVM. So they feed that into the neural networks because it's quite straightforward. Neural networks is good at classification. And SVM used for classification. Why not just use them for classification, right? So the bounding boxes regression can also be done automatically because as when I first to start to introduce neural networks, you see we can convert that regressional line into a very simple neural networks by putting layers, right? That's the examples we use. So the bounding box regression is a very simple case. It's just several numbers. It can be converted into some fully connected layer very easy, very easy way, right? So they can replace that part and then network figure out the regression by itself. So you could see here, you just have to run random sampling, feed them into there, and classification and regression will be done by the neural networks by itself. That's the reason to make it fast than the original RSN. Okay, I guess this is quite straightforward, right? It's easy to understand. And then, however, there's still one disadvantage there. Anyone want to try for this? Because later they develop a faster RSN then. They'll keep doing that. What's the disadvantage right now? It's still not that efficient. But why? What are bottleneck right now? It's already very simple and straightforward, but we still have a bottleneck. Okay, maybe tell you the bottleneck is here, random sampling. As I mentioned, random sampling, have to check the objectiveness for all the proposals there. That's a very time-consuming process. So still they rely on those region proposal. And so it's not end-to-end in that sense. Because you need to run additional random sampling rather than feed it into neural network directly. So the vast RSN. Oh, It's not random sampling. I use the wrong term. It's selective search. What I mentioned a lot of times about random sampling, because it's the random sample and evaluate it. But the right name is selective search. Correct. So what I said, random sampling is actually selective search. Sorry for that. So the selective search evaluate objectiveness prior to the deep learning. So take another time and the faster RSN trying to adjust that problem. So what they're doing is quite simple. They don't rely on the region proposal by selective search. They feed that image into neural networks. You get a feature map like what we have done previously. However, we don't have the region, but we can actually find the region here. There are region proposals networks. You can consider they predefine something called anchor regions, meaning like they define the shape and locations, they randomized distributed over that image. Because what you're looking for is not an exact bounding box. What you need are candidates for bounding boxes, and use these candidates to regrade that true running box, right? So your sub-region is not necessarily match the objects you're looking for. So in that case, you can predefine a lot of regions here. Then for each of this region, you take out their features for classification. Then in the same way, there are some regions will give you a label, for example, the person, right? Then you take out all those has prediction for person, because basically you have to cover a majority part of that person to make a prediction of person, right? Meaning like those bounding boxes, you cover that region. Then after that, it goes back to the same. You have the proposal, some kind of candidates found, then you can run the regression to find the right bounding box for you. And by doing that, you don't have to run a selective search. Then it's right now end to end. You feed the image, and you get the result at the end. So that's a faster RSNN. Okay, is this clear enough? Right? Okay, quite funny. A series from the RSNN to fast RSN to faster RSN. Sure. So, but interesting development. Then the latest RSNN here is the mask RSNN. Now, they're going to give you segmentation rather than bounding boxes there. So you could see they have been changed. The fast RSN is object detection, and mask RSN is not object detection. It's a semantic segmentation. So, because it's kind of much more complicated and on that topic, and also we're running out of time. So I will like to skip the details of the mask RSN here. Just let you know we keep developing it for better use. And I guess that's what I'm going to say today. I actually gave some information here and link it. If you're interested, you can read it. They are actually have done a lot of alignments for the regions. So I'll skip the detail here. Sorry for that. So because I just want to take some time to mention the assignment 2. You will find assignment 2 very soon. From Blackboard. So you will find it from the assessment And this is assignment 2. And there are requirements, and if you download it, it's almost the same like previous day, but the task is different. So what we're going to do here, so the task is to develop an algorithm, a model for a campus tour guide. Meaning like when people take a tour, campus tour here, you can use the app to either take a photo or just hold it. You can see the information about different buildings. The building in the camera will be recognized and give you some additional information like the name of that building, designers, office location, or something like that. Anyway, information is not important. You can put whatever information you're interested. So we're going to develop a model algorithm for support to make that app possible. So first of all, you're not required to develop a complete app. You don't need to develop an app. You're developing the algorithm and models for such kind of app. Okay. But if you are able to develop that app, that will be good. You will have bonus there. Yeah, maybe if your app work, maybe we can recommend that to the university. It's in the future when people are taking the tour, they can use your app. Yeah, that will be perfect. So anyway, so here is a task. And you will find this question very soon. And here's an example app. And so I guess the task is very simple, right? You have to figure out a way for doing it. There's something in our previous tutorial. We have provided some kind of code maybe can be used here. And I can talk about that a little bit during the makeup lecture tomorrow. Right? Okay. But in between, you can think of it and how to do it. Okay, that's it. Yeah. So, there any question you want to ask?
Where is the makeup lecture going to be held?
Oh, I will say the announcement. Probably tomorrow morning, tomorrow night. 8, okay. 8, okay for you guys?
Is it going to be in person?
Oh, no, online. I guess that'll be online. Not sure if this is available, but online might be better during night. Okay? Is 8 p.m. a good time? A good time for you? Or you want to make it 9? Okay. Which one will be better? 8 or 9? Any idea? In that case, 8 will be fine. We just make it 8 in that case. Okay, that's it. And see you online tomorrow in that case. Okay, bye. Thank you.
在一起不一定是空的。